Hello everyone. Today we're looking at question number 6. So a closed room 20 meters by 8 meters by 3 has a volume of air, which is multiplication of these three. Volume V of air. It loses heat to the surroundings at a rate of AHT minus TS. The heat capacity of the air is CV and density is rho. A controller manipulates the power Q of a heater in the room operating at a point of 20 degrees Celsius. What is the heat that is required to keep the temperature at the operating point? Plot open loop response, design a PI controller, and then plot the closed loop response. So first we will calculate our preliminaries. V is 480 meters cubed. So that's the multiplication of these three numbers. And as for the heat transfer area, we're only considering heat transfer area from the walls of the room. So that's why we're getting 20 plus 8. That's the long wall plus the short wall. We have two pairs of a pair of each. And then each one of these is 3 meters high. So hence 20 plus 8 times 2 times 3, 168 squared meters. And now we look at the first law of thermodynamics. So the change of energy or thermal energy in the room is equal to heat input minus heat output. The derivative of U with respect to time, U is rho V CV times T. These are constants, so they can come out of the derivative term, and we have T, which is our independent variable here. Q minus AH times T minus TS. TS is the temperature of the surroundings, which is 10 degrees Celsius here. At steady state, there is no difference in this term, so this would clear out, becomes equal to 0. And because we're talking about steady state, now Q is called Q star, so the steady state heat input, and T star is the steady state temperature. Hence, Q star is equal to AHT star minus TS, and that is 3,360 watts. So that's part A of this question. Next, in order to go through the rest of the question, we should work with deviation variables. This will make the problem statement slightly friendlier. These are our deviation variables. So Q star is Q minus Q prime. In other words, Q is Q star plus Q prime. Rearranging this. We do the same with temperature as well. Now we plug in Q and T into our governing equation. So we can see T star plus T prime plus T star here, Q prime plus Q star, T prime plus T star. For the time being, this seems to be more expensive, more complex than before. However, first of all, this is a derivative, and T star is a constant, and it's a term on its own. So this will be derived on its own, and it would give out a 0. So we can just remove it right now. Second of all, if we look at this term, we can split it into two parts. AH T star minus TS, and this has a negative sign. And AH T star minus TS is equal to Q star. That is the equation that we got here. In other words, this is equal to 0. So Q star would cancel out with these two terms, and we would be left with Q prime minus AH, and that's what's shown in this part here. T star is gone, Q star minus AH T star minus TS is gone, and we're left with this part of the equation, which is slightly less complex. Let's take the Laplace transform of this. We will look at this in the next slide as well. Okay. So for the Laplace transform, the derivative term gives out S T bar of S. So that's the Laplace transform of a derivative, S times the Laplace transform of the function minus the initial value of the function. And we're looking at a case where the system starts at the steady state temperature, and then we're looking at the response of the system to changes happening. which means t prime of 0 is equal to 0. And that's why this term is cancelling out. The rest of the equation is quite normal, so q prime became q bar, t prime became t bar. Rearranging these terms, I want to calculate the ratio between t bar and q bar. So we're just moving terms left and right, and then we're going to take t bar as a common factor and rearrange terms to get t bar divided by q bar, and that would give us this equation here is equal to 1 over a constant times s plus a constant. And this is a typical equation of a first order system, and this is something expected from our governing equation. Rearranging the constants, I want to have this as a 1, so we're dividing by ah. So 1 over ah divided by rho vcv over ah times s plus 1. And in this form we can see it's k over tau s plus 1, a typical response or typical transfer function of a first order system. Now k is equal to 1 over ah, so 168 times 2, the reciprocal of that, 1 over 336, is 2.3 times 10 to the negative 3 Kelvin per watt. So almost 3 millikelvin per watt. It's a very small number. For calculating tau, there's something that we need to pay attention to, which is CV. CV is given as 0.72 kilojoule per kilogram Kelvin, but the SI unit for energy is joule, and we're working with joule and watt, not kilojoules and kilowatts. So we multiply this by 1000, so it's 720. And this gives us a time constant, or tau, of 1234.3 seconds, which is 20 minutes and 34 seconds. Now you might be looking at this note here. Why is it stuck on this slide? Well, for part B of this question, we're looking at q bar of minus 10 divided by s. Essentially, a 10 watt reduction in heat input is a step function for heat input, and the height of the step is minus 10. Hence the Laplace transform of that function would be minus 10 over s. So q bar, we took the minus 10 watt reduction in the heat input as a step function. We took the Laplace transform of that, and now we're going to plug that into this equation, to this one, to see what is going to happen. Now we took q bar to the other side, so t bar is k over tau s plus 1 times q bar. Okay, what are we going to do next? So q bar, now we're making the Laplace transform of this. Now we said that q bar is 10 over s, and the 10 here we're calling it q prime. So q prime here is equal to 10. It's just the number, sorry, just the number minus 10. That's q prime here. That's the height of the step function, which is a constant. It's not a function of time. It's a constant here in this instance. Now, k over tau s plus 1 times s, and I'm taking the tau outside so that I have 1 over s plus 1 over tau, which matches our table here for the inverse Laplace transform. This is in the frequency domain. We want to transform it back to the time domain, and we use this formula here, 1 over s plus a times 1 over s plus b. Looking at this, these are constants. 1 over s plus a, so a is 1 over tau and b is 0. Plugging things back in place, so kq prime over tau stay the way they are. 1 over b minus a times e to the minus at minus e to the minus bt. b is 0, so this term will not be 0. E to the power 0 is 1. Now we have a negative sign here that comes out as here, and 1 over tau in the denominator becomes tau essentially, and it cancels out with this tau here. So we have kq prime minus kq prime times e to the minus t over tau minus 1. Let's bring in this negative sign here, so we get 1 minus e to the minus t over tau, and that is our response curve. Kq prime times 1 minus e to the power t over tau minus t over tau. But that is t prime, that's the deviation variable. Let's calculate the temperature itself, which is equal to t star plus t prime, so we essentially add 20 to this equation. Now I'm plugging in numbers, so q prime is minus 10 and k is 1 over 336, and we have this equation. In the next slide we will look at how this equation looks like on a graph, but for the time being let's calculate the steady state temperature, and by plugging in infinity for t, so e to the minus infinity is 0, so this whole thing cancels out, so it's 1t minus 10 over 336, which is 19.97. Our heater has an output of 336 watts. That's what we calculated on the first slide. Reducing that by 10 watts will not really make a big of a difference. The difference made is 0.03 degrees Celsius. However, the way we get there from 20 to 19.97 doesn't care about the temperature difference. We will always be doing that using exponential decay function. Now if we look at this function, let's look at this equation here. I'm just rearranging numbers, so I'm getting 19.97, which is 20 minus this part here, plus 0.03 times e to the minus t over tau, and this became a plus because we have a negative sign here going in, interacting with this to give us a plus sign. So this number gives us the floor here, which is 19.97, and the blue curve really is e to the minus t over tau. The height of the curve is 0.03, and the shape of the curve is dictated by e to the minus t over tau. Tau is our time constant, and what it essentially means is that every tau is measured in seconds. The curve would cover about 63% of the temperature difference it is going to cover. So it will cover 0.03 degrees Celsius. 63% is done in the first tau, so we have 37% remaining. Out of the 37% remaining, 63% is done in the second tau, and whatever is remaining, 63% of that is done in the third tau, and so on. Now, whenever you see a first order linear system, you can expect a curve that looks like this. And to characterize this curve, you only need three things: initial value, final value or steady state value, and tau, and basically just plot the curve between those. Now if the initial value is lower than the final value, then the curve would look like 1 minus this. It's the same shape but going upwards, which we will see in the later part of this problem. Design a PI controller for this system that regulates the temperature in the room. We will take a standard first order plus time delay model. K e to the minus theta s divided by tau s plus 1. Now, we're not really interested in the time delay. It's just the model that we picked. It has that. So we'd set the time delay to be 0, and we would get k over tau s plus 1. We already know k, we already know tau of our system. Now, we can use the direct synthesis method or the IMC method. In both cases, we will get exactly the same controller because we don't have any time delay. And what these methods tell us is that we basically set tau I to be equal to tau of our system. And we set Kc to be 1 over K T over Tc. Tc here is our desired time constant of the system. So what I used to call system up until this point now is going to be called the process. So tau that we calculated is tau of the heat transfer process. These are the characteristics of our room. That's tau of the process. And now tau I is the time constant for the integrator part of the controller. Tau C is the desired time constant for the resulting system, which is comprised of the controller and the process. Kc is the is the proportionality constant for the proportional component of our controller, and K is K that we have calculated for our system. Let's set our, well, it's our goal, not our goat, to make the system 3 times as responsive as an open loop system. So tau C is equal to tau over 3. That's what it means. 3 times as responsive. Tau C is 3 times shorter than tau. And plugging in numbers, we can see that tau I is equal to tau, that's this part here, which is 20.57 minutes, or 20 minutes and 34 seconds. And Kc, because tau C is tau over 3, plugging that here, tau over tau C is equal to 3. So Kc is 3 over K. K is 1 over 336, so that gives us 1008 watt per Kelvin. Something that I want to point out is that K had a unit, or has a unit, of Kelvin per watt, while Kc has a unit of watt per Kelvin. They're opposite units. They're the inverses of one another, which makes sense. One of them defines the sensitivity of the system to heat. So the system responds to heat that we bring in. The result is a temperature. The controller responds to the temperature input, and the output is the heat. So they are reciprocal of one another. Let's verify the response of the system to a step change of set point. So we want to plot the system response, so we're introducing a change of set point. So set point was set to 20 degrees C before. Now let's change that to 25. Now we have a step change of our set point. So the new value for our new set point is 25 degrees C. Expressing that in a deviation variable, it's plus 5 as a step function. Now T double star prime, T double star is that step function. T double star bar is the Laplace transform of that step function. Okay, so that is the definition of our system response, and calculating that we will use this equation, which has been demonstrated in your book. Gc is the transfer function of our controller, Gp is the transfer function of our process. Our controller is a PI controller, so that's how Gc looks like. We don't have a derivative component, so we don't have a tau d component. We just have the proportional part and the integrator part. And this equation is as per our initial analysis, as well as the first order plus time delay model. They are both identical. Now, something worth noting, tau I is equal to tau Kc times K is equal to 3, so that's what we got from the previous step. Now we want to add the 1 to 1 over tau Is. So to unify the denominators, we get tau Is plus 1 over tau Is. And tau Is plus 1 and tau S plus 1 are exactly the same thing, because tau I is equal to tau, and hence they can cancel out. This happens both in the numerator and in the denominator, giving us this simplified form. In rearranging variables, we get 1 over tau divided by kg.K times s plus 1. And if we look at this, this is the same form as we originally had for our system, except that our new k that encompasses both the controller and the system is equal to 1. And tau is significantly smaller, because kc times k is equal to 3. So tau has been slashed in half. What does it mean that we have a k of 1? It means that one one unit change of our step function would result eventually in 1 unit change in our output. So if I change the set point by 1 degree Celsius, I expect the final steady state output to change by 1 degree Celsius. It's expected to work that way, right? If you increase the set point by 1 degree Celsius, you expect the temperature eventually of the house to go up by 1 degree Celsius. Now let's calculate tau bar, and a couple of things that I've done here in the first step. You can see that tau double star bar has moved to the right side, and it's here, and now it's divided by s, because that's the Laplace transform of the step function. The height of the step function is tau double star, and the Laplace transform of that is t double star divided by s. In the next step, we're trying to simplify how the equation looks like, and I'm taking kc times k divided by tau as a common factor. I want s to have no coefficients here, so that I can use the table that I have used before. And if you remember this part, so if I have 1 over s plus a times s plus b, then the Laplace inverse transform is 1 over b minus a e to the minus at minus e to the minus bt. And that's what I'm trying to get here. Okay, so the Laplace inverse transform gives us the following. T prime, which is the Laplace inverse of t bar, is equal to t double star, which is essentially a constant here, times kck over tau. These are the constants that we have. Now 1 over b minus a is 1 over 0 minus a is this term here, kck divided by tau, times e to the minus at minus e to the minus bt. This looks really complex, but it really eases out at this point, because this term here is exactly the same as this. So we have tau t prime is equal to t double star times 1 minus e to the minus t of essentially our new tau, like, right? It's e to the minus t over, this is tau c. And as we said before, with a first order system such as this one, and even with the controller, this is still a first order system because of the way the controller is behaving. Looking at this, all we need to characterize this is our initial value, final value, and tau, our time constant, which is basically tau over 3 here. Now, for a step change from 20 to 25 degrees C, t is equal to, now we're breaking t bar into t star and t to get t. T bar is this equation here, that's here, and t star was the 20 degrees Celsius from the beginning of the question, from slide number 2. So we have 20 plus 5 times 1 minus e to the t over nu tau. Initial temperature is 20 degrees Celsius. Final temperature is 25 degrees Celsius, and the way we go there is exponential decay. Now we can see the 411 seconds basically is tau over 3, which is 6.9 minutes approximately, almost 7 minutes. And if we look at this curve, it's a typical exponential decay. Even though it's going up, the exponential component is decaying. This is not exponential growth. Exponential growth grows up to shoot into infinity. And if we look at this, we can see our starting point is 20 degrees C. Our final temperature, or the steady state temperature, is 25 degrees C. But now in this curve, we reach there way faster. So after 7 minutes, we cover 7 minutes would be right around here, and we would be covering 63% of the temperature difference, because that's the definition of time constant. And within a time period of 30 minutes, we would be very close to our steady state temperature. 35 minutes is basically 5 tau, and we're getting very close to the final temperature. If we compare that to the previous case, we'll get there in a moment. Here, after 30 minutes, that's slightly more than 1 tau. That's less than 2 tau, and we still have a long way to go. In terms of, like, with respect to the total change in difference, this was a minuscule change, so it didn't make a big difference. But you can see the system has become way more responsive. So looking finally at this curve, beyond that the curves are essentially identical. They are both exponential decay, going from initial temperature to final temperature. Thank you.